Good afternoon, friends. Last time we are discussing about the relationship between two transforms, the real part and the imaginary part of the DTFT, that is x a to the power j omega. That means, if the real part is given, how do you determine x I, imaginary part, or given the imaginary part, how do you compute the real part, all right. So, that was our problem, and we established the relationship x n can be decomposed into an even part and an odd part, and the real part of x e j omega is related to the even part if it is a real sequence, and the odd part is related to the imaginary part. Now, with this, last time we established the relation x I e to the power j omega was minus 1 by 2 pi minus pi to plus pi x r e j theta cotangent omega minus theta by 2 into d theta. That is, given the real part of the frequency transform, you can compute the imaginary part. Similarly, the real part was computed from the imaginary part from this x I e to the power j theta cotangent omega minus theta by 2 d theta, plus what is missing in the odd part, the initial value x 0, all right. So, this is an additional information that has to be known a priori, and you can use it with the imaginary part. So, we discussed about this cotangent function. Suppose you are having, you want to compute it for different values of omega. So, you take theta, suppose x r e to the power j theta is like this. Maybe like this. I am just hypothetically taking a function like this. Similarly, it will have its image on this side, and cotangent omega minus theta, if I keep on varying omega, take one value of omega, when omega is equal to theta, this becomes cotangent 0, and cotangent 0 is infinity. If it is minus 0, that means 0 from the left side and from the right side, then the function will be somewhat like this. Maybe like this. One will be going to the positive side, the other one will go to the negative side. Then this is an improper integral. You cannot compute this because one part of it tends to infinity at a particular value, all right. It is not analytic. In that case, how do you evaluate this integral? If you assume this omega minus theta to be very, very small, let us take omega minus theta as a quantity epsilon. Okay. So, if you take a very small value of epsilon, then from the positive side and from the negative side, you see a function is going like this, say, going to infinity, and another function, say it is like this. We are taking the products. So, this value multiplied by this and this value multiplied by this, when it is tending to infinity, it is tending to say plus 10,000, and at an equispaced point here on this side, it will be minus 10,000. Okay, cotangent function tending to when that argument is tending to 0, a very small value of epsilon, then it will be plus a very large value and minus a large value. And if we bring it very close, epsilon is tending to 0, if we bring theta very close to omega, in this range we can assume the value of the other function, that is xr, to remain practically constant at that value. So, if we assume xr to be constant at that value of omega, j that particular value of omega, okay, omega is equal to theta at this point, then the plus very large quantity multiplied by this and minus this quantity, they will cancel each other, all right. So, by taking points at other than this location very close to omega equal to theta, you can evaluate the product and evaluate the area under the curve. You can similarly calculate this, leave aside a very small zone, you drop it, you skip that point, okay. You can have computationally, you can take point by point summation, integration means sum of these products point by point and skip that point. This is one way of evaluating an improper integral of this type, then you can calculate this, but it is a tedious job, okay. Can we surmount this problem by taking help of DFT, that is instead of instead of computing this over all values of omega, we take discrete points, okay. Let us see how we can do it. Suppose we can do it. Before we go for that, let us see what will be the Z transform of x for which the real part is given. It can be shown if we can make this convergent, this summation, this product of xr into this integral, if it can be shown, this is an improper integral, but if we can evaluate it by this method, then we can, since xi and xr they are finite now, we can evaluate xz, all right. That will be equal to 2 pi j, that relationship z plus v by z minus v dv by v, okay. Now, how to get this? We will prove it. Let Wn be the product of two functions x1n into x2n, two sequences. Then Wz will be 1 by 2 pi j x1 v, this is integration over this closed path C, x1 v into x2 z minus v v to the power minus 1 dv, okay. That means, if you know Z transform of x1 and x2, then you can always write, having a running variable v and taking the product, you can calculate Wz, okay. It is basically convolution in the Z domain. This is a standard relationship. From here we will establish this relation. Now, in our case xn is 2 into xen, this is the relationship that we established last time. You remember, in terms of the even function we can write the original function xn. Therefore, xr Z, which is Z transform of x e n, Z transform of u n is Z by Z minus 1, and x 0 we know is 1 by 2 pi minus pi to plus pi from the DTFT. This is known, is it not? So, these are given to you. X z will be 2 into, I take Z transform of both sides. So, 2 into Z transform of this product, okay. Z transform of the product is given by this. Similarly, x 0 into delta n, x 0 is a constant which is known, and Z transform of this is 1, okay. So, x z will be 2 into 1 by 2 pi j x r, just x 1 into x 2. So, this is x 1, this is x 2. So, corresponding to this is x r, all right. So, I will put v, is that all right? Okay. And then z by z minus 1. So, z should be replaced by z by v, is it not? So, z by v divided by z by v minus 1 into v to the power minus 1 into dv, okay, minus 1 by 2 pi j this integration x naught delta n gives me 1. So, this integration gives me x r v dv by v, all right. So, that is equal to 1 by 2 pi j x r v. If you simplify that, this one 2 into z minus z minus v minus 1 into dv by v, okay. Minus 1 comes from this term x r v is common. So, this is dv by v only, that is equal to 1 by 2 pi j x r v. If you simplify this, this will become z plus v by z minus v into dv by v. This is what we wrote in the beginning. So, this is the proof. Let us work out an example. Let x r be given 1 minus alpha cosine omega by 1 minus 2 alpha cosine omega plus alpha squared. Alpha magnitude is less than 1 and it is real. Compute x z. Okay. Now, before we go for the evaluation of x z, let us express this in the exponential form of e to the power j omega. Cosine omega I can always write in terms of e to the power plus j omega e to the power minus j omega. So, let us do that. So, the given expression will be equal to 1 minus alpha by 2 e to the power j omega plus e to the power minus j omega. Is that so? 1 minus alpha into e to the power j omega plus e to the power minus j omega, okay, plus I can write alpha into e to the power j omega into alpha into e to the power minus j omega. Alpha square can be written like this, e to the power plus j omega and e to the power minus j omega will give me 1. So, I have written this alpha square into 1 in this form. So, that I can write this as equal to 1 minus alpha by 2 e to the power j omega plus e to the power minus j omega divided by 1 minus alpha e to the power minus j omega into 1 minus alpha e to the power plus j omega. Okay. So, if you now compute x z, it will be 1 by 2 pi j 1 minus alpha by 2 x r e to the power j omega is replaced by v, is it not? So, I will write this as v plus 1 by v, okay, and this one will be 1 minus alpha v 1 alpha v to the power minus 1 into 1 minus alpha v, okay, into z plus v by z minus v into dv by v. I have just used the earlier relationship that we established. Okay. So, 1 by 2 pi j, if you simplify this, multiply throughout by v, the numerator becomes v minus alpha by 2 v squared plus 1, is that all right? If I multiply by v, this becomes v squared plus 1. If I multiply this by v, then this becomes v minus alpha into 1 minus alpha v into z plus v by z minus v into dv by v. Okay. What are the singularities? V is equal to alpha within the unit circle, V is equal to alpha is a pole when this function blows up. The other one is V equal to 0 because of this, and these are inside the unit circle. Okay. If they are within the unit circle, then x z, calculate the residues at those poles, then it will come out to be minus alpha by 2 z by minus alpha z plus alpha minus alpha by 2 into alpha square plus 1 into z plus alpha by z minus alpha into alpha. Okay. Divided by, okay, I will put it here, into 1 minus alpha squared. I am putting alpha is equal to v. So, this becomes 1 minus alpha squared. I am calculating the residues. Then first you multiply by v minus alpha, that function, and then put v equal to alpha, is it not? So, v equal to alpha if I put, so I get from here 1 plus alpha square, 1 plus alpha squared, and so on. Okay. So, these are the some of the residues. So, finally, if you add up, you will get z by z minus alpha, which is nothing but 1 minus alpha 1 by 1 minus alpha z inverse. So, this is x z. After adding all this, you will find lot of terms will get cancelled, okay, and you will be getting a reduced form. Let us take another example. X real e to the power j omega is 2 minus 2a cosine omega. Determine the imaginary part. Okay. Now, this I can write as 2 minus a into e to the power j omega plus e to the power minus j omega. Okay. What will be the corresponding even sequence? What is its inverse? What is its inverse DTFT? 2 will give me 2, a constant will give me 2 into delta n, is it not? Minus a into e to the power j omega. So, that will be a into delta n plus 1 minus a into delta n minus 1, is it not? A delta function, what will be its DTFT? 1. If I shift it by one step, that is delta n minus 1 will be e to the power minus j omega. The sequence is 0, 1, 0, 0 and so on. What will be its DTFT? It will be e to the power minus j omega. If I shift it by 2 steps, it will be e to the power minus j 2 omega and so on. If I shift it on the other side, it will be plus j omega. So, it will become delta n plus 1. Corresponding to this term, it is delta n plus 1. Corresponding to this term, it will be delta n minus 1. Is that okay? So, this is XEN. Now, Xn, so if I draw XEN, it looks like this: 2 into delta n, this is 2, minus a delta n plus 1. So, at minus 1 it is minus a and plus and minus a delta n minus 1. At 1 it is again a magnitude of minus a. This represents this function, all right. Mind you, even function, last time we discussed, even function and odd functions will be extending on both sides, is it not? When you take a real causal sequence only defined in the positive range, positive region of time, discrete time, the even part and the odd part, if you compute from there, even part is 0, the original sequence is having 0 values in the negative region of time. So, if you take the average, you will get some values on the other side. So, even part will be XEN will be extending on both sides. Similarly, X odd. So, this is XEN. Now, how do you recover Xn? Xn we know is twice Xen into Un minus Xe at 0 into delta n, is it not? And this we are using quite often. So, how much is it? 2 into Xen is 2 into delta n. Just now we have got 2 into delta n minus a into delta n plus 1, okay, minus a into delta n minus 1, whole thing multiplied by Un minus Xe0, Xe0 is 2, so 2 into delta n. Correct me if I am wrong, is it all right? So, how much is it? 2 into 2, 4 into delta n, mind you it is multiplied by Un. So, delta n plus 1 does not have any chance, because it exists in the negative region of time and it is multiplied by un, which is having a 0 value here. So, this will be blocked out. So, it is 4 delta n, okay, minus 2 a delta n minus 1 minus twice delta n. So, how much is it? 2 into delta n minus twice a delta n minus 1. This is the sequence. Okay. If you want, you can calculate x z also from here. What is the imaginary part and what is the DTFT of this? Therefore, x omega will be 2 into delta n. So, 2 minus twice a delta n minus 1. So, that will be e to the power minus j omega. So, this is x a, and what is its imaginary part? You can compute from here. Imaginary part will be only from here, will be minus, and minus will make it plus twice a j times twice a sin omega. Is it all right? Now, so far we have considered a causal real sequence. Okay. Now, this can be applied to a finite length sequence, causal sequence. Okay. Now, we can very easily, since it is a finite length, we can very easily represent this by a periodic sequence taking only one period of this as this sequence. All right. So, we will create an artificial sequence where one period will be embracing only this particular part along with some padded zeros. Let us have a stretched sequence, that means the given sequence we stretch it in time domain by putting some 0 values, and then that is made one period, and let us repeat that. We take advantage of a periodic sequence where discrete Fourier series can be computed, and discrete Fourier series is equivalent to discrete Fourier transform. If you consider one period, the expressions are identical. What is the difference between a discrete Fourier series and a discrete Fourier transform? What is the difference between Fourier series and Fourier transform in the continuous domain? Fourier series you take for a periodic function. Okay. If a function is periodic, say like this, then we go for Fourier series. You get certain lines. If this is xt t, I get xf at some values of f corresponding to this period, we call it fundamental. So, we get, if that is called f naught, then we get some values f naught, twice f naught, thrice f naught, etc. We call them harmonics. Okay. In periodic, in case of periodic functions. If this is an aperiodic function, then xf is no more discrete, it is a continuous function. All possible frequencies are present when xt is an aperiodic function. This is xt. So, corresponding to that you have a frequency transform which is continuous, not lines. Okay. Now, in the discrete domain, if you have a discrete sequence of finite length, suppose this is a sequence, after that it is all 0, it is not periodic, then what will be its frequency transform? X e to the power j omega in the discrete frequency domain we get a continuous function, sorry, in the frequency domain we get a continuous function. But if this is discrete and periodic, if this is, we show a periodic function by this tilde. So, if it is like this, then we get on this side also a periodic function which is discrete. It may be anything, we do not know. This will be basically discrete versions from here, these values. Okay. Again repeating. So, this is a periodic function in the discrete domain. Corresponding Fourier series is called discrete Fourier series. In the frequency domain also, we will get only discrete frequencies and coming periodically. All right. Unlike normal Fourier series, in a normal Fourier series you have, because it is continuous, you have only the lines going up to infinity. Okay. And when it is discrete, instead of a continuous function, we get this periodic, this will be coming periodically. Okay. When this is discrete and periodic, this will also be discrete and periodic. So, these are the types of functions that you get. So, this is known as discrete Fourier series. Now, if we do not have a periodic function, if you have just one sequence, then this can be represented, instead of representing it by in the frequency domain by periodic functions like this, we can represent this by only that many frequencies, maybe like this. There are 4 points, so you will get only 4 frequencies, that is good enough. That will be describing basically the values at these points, and at these points if the values are known, then you can describe with these 4 points this entire function, these 4 definite points in the sequence. All right. Basically, we need so many frequencies to represent the original time function. Original time function is discrete, it is a 4-point sequence. So, I do not need more than 4 frequencies, I do not need so many frequencies to represent this. Okay. So, this is known as discrete Fourier transform. All right. So, discrete Fourier series and discrete Fourier transform, these magnitudes are identical, only thing here it is periodic, here it is just one set, one of the periods we are taking. So, basically the relationship is, so far as the mathematical relationship is concerned, they are identical. So, for discrete Fourier transform, we just put a tilde k equal to 0, 1, 2, 3 if it is a 4-point sequence, and for DFTs we write xk, but the expressions are identical. Okay. So, we are considering a discrete Fourier series, that is we are taking one sequence, padding it with sufficient number of zeros, we will see how many zeros are required minimum, and then we are creating a periodic sequence. Now, we started off with a causal sequence, now we are going to a sequence, only a part of it is this sequence. So, that one is a periodic sequence. So, it is a pseudo causal sequence or periodically causal sequence, it is a misnomer. Periodically causal, a causal sequence cannot be periodic. Periodic means it exists also in the negative region of time, whereas a causal sequence will be always in the positive region of time. So, we are calling it periodically causal or pseudo causal sequence. Okay. Periodically causal sequence, and let us see what is that sequence like after appending with zeros. we take this periodic sequence as x n modulo n. The moment I write modulo n means it is periodic, you keep on subtracting n, the magnitude is repeated after every n steps, all right. So, I can write x tilde n as x even part and an odd part, okay, where x even part x tilde is x n. These tilde marks means they are all periodic functions. Okay. Similarly, the odd part is x tilde n minus x tilde minus n by 2. Okay. So, we append the sequence x n, original given sequence x n, by a few zeros. Such that we get a length of sequence length of n, okay. We assume n to be even, and up to n by 2 it exists, and that means x n is made 0 between n by 2 and n, and 0 to n by 2, sorry, n minus 1, and 0 to n by 2, 0 to n by 2, it is having the same value as the given sequence. Okay. So, let us see what x n will be like. Suppose you are given a sequence value, say 2, 1, minus 1 and okay, 3, all right, 3, 1. So, I will try to go to an even number such that this becomes half, this point becomes half of this. This is 0, 1, 2, 3, 4. Okay. So, 4 multiplied by 2, 8. So, 5, 6, 7. This is an 8 point sequence. So, I create an 8 point sequence by appending 3 zeros, all right. 8 divided by 2 is 4. So, the index number 4, that means on this side there are 5 non-zero points and 3 zeros. Mind you, they are not equal in number, it is up to n by 2. N by 2 including 0 means it is more than half by 1, all right, and this is less than half by 1. Is that all right? The index number is 4, 8 by 2. Okay. So, I have an 8 point sequence. This is our 1 period. If this is the sequence given, then we create an artificial sequence with padded zeros, and this is 1 period. Now, this keeps on repeating 2, 1, minus 1, 3, and then again 1, this is 1 set, and so on, again zeros. Similarly, on this side zeros and so on. Okay. So, x n is 2 times x c n for n is equal to 1, 2 up to n by 2 minus 1, and is equal to x c n at n is equal to 0 and n by 2, and equal to 0 at n is equal to n by 2 plus 1 up to n minus 1. Is that all right? let us verify whether this is all right. Let us take some values of x n and x minus e n. Okay, let this be, let me have a sequence like this: 6 will compute this, 2, 4, they are not drawn to the scale, that is why I am writing the values, say minus 4, then 3. Okay, this is 2. Then there will be 3 zeros. I have taken a 5-point sequence. Okay. So, this is x n tilde. This was x n. So, I have padded with zeros and then I make it periodic. So, this is the periodic sequence. And so on. Similarly, on this side 0, 0, 0 and so on. Before 0 this is 6, so then this is 3, then this is minus 4 and so on. It continues on this side. So, what will be x tilde minus n? Because I will add the 2 and divide by 2, I will get the even part. So, from x e n, what will be x e minus n? It will be 6, then go from this side 0, then 0, then 0, is it not? 0, 0, 0, then 3, then minus 4, correct me if there is any slip, 4, then 2, then 6, and that repeats. Is that all right? Now, if you take the average, that will give you x e n. It repeats on this side also, 6, 2, 4, minus 4, 3 and so on, zeros. So, take the average and then tell me what will be x e n like. So, x e n, if you permit me to draw x e n, 6 plus 6 by 2. So, that will be 6. Okay. Then here you see the advantage of padding zeros is 2 plus 0 by 2. So, it will be halved, all these values will be halved, okay, except at this point, the 5th point, which is n by 4, whose index number is n by 4, that will be again 3 plus 3. Is that all right? There is no midpoint for an even number sequence of say 8 points. There are 5 on this side, 3 on the other side. Okay. So, this will be half of 2 plus 0, that is 1, then this is half of 4 plus 0, so 2, this is 1, then minus 4 and 0, so minus 2, then 3 plus 3 by 2, so that is again 3. Okay. Then on this side is 4 plus 0 by 2, 2 plus 0 by 2, all right. So, this side again it will be symmetric. Is that all right? Okay. What will it be? It will be 4, am I all right? 4, so 2, then 1, check if I have taken 2 plus 1, 6, 2, 4, minus 4, 3 minus 4 3 0 0 0. Is it all right? Okay. So, 3 plus 3. So, immediately after that, that should be, oh, it should be minus 2. Yes, minus 2, and then it becomes plus 2, then plus 1. Okay. Then again 6. So on. You can have just an image of on this side. All right. I have not really drawn to the scale. Okay. That is why I have written the magnitudes. You will find it is symmetric about the midpoint. It is also symmetric about the starting point 6. All right. This will be XEN. That is why I wrote it is equal to XEN for 0 and n by 2. At this point and at this point, the values of Xn and Xen are identical, 6 and 3. Okay. And at other points it is just halved in magnitude. So, twice of that even part gives me the original Xn sequence at other points, and it is 0 for n by 2 plus 1 to n minus 1. Original sequence, it is only for this part. So, even if Xn Xen is extending up to this, but it is twice of Xen only up to this point, because original sequence otherwise it is all 0. Though Xen is having these values, that means if I add it with odd part, that should get cancelled and that should generate this. So, you can write the odd part. How much is the odd part? Odd part at this point 6 plus how much will be equal to 6? It has to be 0. Odd part, the central value is 0, and how much should be added to 1 to get 2? It will be just 1 again, because it is half of this. So, up to this point it will be same as Xen, 1, 2 and minus 2, and at this point it is 3 is equal to 3. So, this value will be 0. Okay. And then at these points the resultant should be equal to 0, is it not? So, whatever you are getting in the even part, negative of that should appear in the odd part. So, it will be plus 2, minus 2, minus 1. Okay. So, you can sketch the odd part once you know the even part and Xn, the original Xn is given. Okay. So, what one may ask, so what you get this. Now, let us see how we compute the function Xn. I define a function un which is periodic, which is equal to 1 for 0 and n by 2. For 0 and n by 2, it is multiplied by 1, the even part multiplied by 1. For these values it is multiplied by 2, and for these values it is multiplied by 0. So, it is these sequences of multiplier 2, 1 and 0 that I write in terms of a function, which is 1 for these values, which is 2 for n is equal to 1, 2 up to n by 2 minus 1, and which is equal to 0 for n is equal to n by 2 up to n minus 1. Okay. Then we can write x tilde n as un n into Xen, is it not? Xen, if I multiply by a function which is defined like this, I will get the product Xn. Term by term I multiply by 1, sometimes 2, sometimes 0. Is it all right? That means, or in terms of odd function, it is only at this point, and that is at 6 and 3, this is 0 and n by 2, 0 and n by 2, these values are missing in the odd part, is it not? When you subtract in the odd part, that is missing. So, I can also write this as x 0 n into u n, okay, plus x at 0 delta n plus x at n by 2 into delta n minus n by 2. Okay. Now, this delta means it is a periodic sequence of impulses at regular intervals, all right. You have to multiply by, that is the first value is to be given, and then at regular intervals of 8 steps, at 3, that is at n is equal to 4, then at 12, etc. I have to also get this value, okay, of the original function. That is not given, I mean that has to be given, then only from the odd function I can recover x n. Odd function has certain values of the original sequence missing, all right, whereas in the even function you just multiply by this. So, I can straight away go for DFT or DFS. As I told you, DFS, basically a part of DFS is DFT. Okay. So, I can straight away take the discrete Fourier series xk. There are 8 points, so I will get 8-point sequence which will be repeated, and xk, which is xrk plus j times xik. Okay. Now, this I can compute from here itself. What is xk? Transform of this, all right. Now, what is this? 1 by n. If you remember, if you are having a periodic sequence, and if you have if you are having the products, see, for a periodic sequence, what is the DFT? It will be also DFS, that will also be a periodic sequence, you can compute that, and then if it is coming in a product form, you can straight away write XR n u, this u is the DFT of this small u, this time series k minus n. Okay. In the frequency domain, it will be convolved like this. In the time domain they are product, so in the frequency domain they will be convolved, and because it is discrete periodic function, so in the frequency domain also you do not have to take the integral of xr e to the power j theta and u n e to the power j omega minus theta and so on, and for different values of omega. You do not have to go in the continuous domain, you can straight away take those discrete points, 8 points. Okay. So, in the next class we will take up how to evaluate this. That means you are having a sequence 1 1 2 2 2, then 0 1 2 3 and then 4, that is 1, then 0 0 0. This is your un, okay, of period n. What is the Fourier transform of this? Say DFT. How do you compute that? We will take it up in the next class. So, it is basically 8-point DFTs 1 2 2 2 2 0 0 0. Okay. Okay. We will stop here for today. Thank you very much.